So what I want to talk about now is the topic of compatible and incompatible variables. And so if I kind of review what we've gone over so far in quantum mechanics is that what we start with some state, psi, and that psi can produce many eigenvalues. So usually what we do is if we want to make a measurement, then what we do is we would apply an operator to the state, which would then produce a single eigenvalue, which we're going to call lowercase omega. If I want to calculate the probability that I'm going to measure this single eigenvalue, omega, then what I do is I calculate the probability from basically this norm squared, where I've taken the full state, psi, and I've projected it onto the single value that I'm looking for, omega, and then I square it. So what I want to think about now is, what if we have two observables, or basically two consecutive measurements? So these two measurements we're just going to kind of label abstractly as omega and capital lambda. And so acting separately, omega operating on psi will give me the eigenvalue lowercase omega and then the state back psi. Or if I operate with lambda, then lambda operated on the state psi is going to give me an eigenvalue lowercase lambda and then the state psi back again. So if I have two consecutive measurements, so let's say I first operate or measure omega, and then after I do that, I measure lambda after I've made my first measurement, then omega operating on psi is going to give me the eigenvalue lowercase omega, and then the state psi, not the state psi, but, it's going to give me that eigenvalue, that eigenvector, omega. So omega operating on psi is going to give me the eigenvalue lowercase omega, and then it's going to line up with that eigenvector omega, which is associated with the eigenvalue. And so now the eigenvalue is just a number, so I can pull it out front, and I get the operator lambda operating on the state omega. If I do that in reverse, so let's say I operate first with the operator lambda, and then second with the operator omega, then I get the eigenvalue lambda, and I'm now in the state of lambda, and then the eigenvalue lambda, you can pull that out front, it's just a number, and then we have omega operating on the state lambda. So if it turns out that these two bases, if omega and lambda are orthonormal, then lambda operating on omega is just going to give me 0, the null. So if these two states are orthonormal with each other, the consecutive measurements doesn't really matter too much. Because either way, when I operate with lambda on omega, I get 0. When I operate omega on the state lambda, I get 0. So either way, if we go basically in either direction, lambda first and then omega, or omega first and then lambda, then we get 0. We get the same result. So let's consider now a different case where we have a simultaneous eigenstate. So let's say we have this simultaneous eigenstate of omega lambda, where now I can operate with both of them. Omega operating on omega lambda gives me the eigenvalue omega and then the state back again, or lambda operating on omega lambda gives me the eigenvalue lambda times the state back again. And so now they're not I'm not going to get the null result. I'm not going to get a 0, and the order is now possibly going to matter. So it may be a difference between lambda operating and then omega, or omega operating first and then the operator lambda. So to test this, what we do is we try both of them and subtract them. So we can have the quantity omega lambda minus lambda omega operating on this simultaneous eigenstate, which is basically the commutator operating on this state. And if this operation is equal to 0, then we can say that these two variables, these two operators, lambda and omega, commute. And so, or another way of saying it is that they're basically kind of the order is independent. It doesn't matter which one I operate first, omega first and then lambda, or lambda first and omega, then the order of operation doesn't matter. So we can classify these variables. So we have compatible variables, and those are the ones where the commutator is equal to 0, or we have incompatible, where the commutator is not equal to 0. So it gives you a non-zero eigenvalue. The third option is everything else. Something that doesn't fit in with the compatible category and the incompatible category. 3 classes where class A now says that we can have simultaneous and basically independent states, eigenvectors. Class B, where the commutator is not equal to 0. In that case, now we have basically a state that cannot be defined independent of those two operators. So they're no longer independent, and so what you have is an example of something like position and momentum, so that when we make the commutation of the operators of position and momentum, then we get something like IH bar. So we'll come up to this when we start talking about the Heisenberg uncertainty principle. But basically what it means is that a measurement of position is now going to lead to some uncertainty in the momentum, or it's going to affect our momentum of the system. Or a measurement of momentum is going to in some way affect the position of the system. And so, what we're going to look for is when we look at the operators, we're going to look and see, do these pair of variables, are they compatible and therefore basically independent of each other? And are they going to be incompatible, where they're going to be somehow tied together? And the compatible ones don't mean we necessarily ignore them, because those compatible operators can lead to things like conservation laws. So if we have a variable that is compatible with the Hamiltonian, we'll show later on that that variable is going to be a conserved quantity. And so, if the momentum is compatible with the Hamiltonian, we'll have conservation of momentum. If the energy is compatible with the Hamiltonian, then the energy will be conserved. And so all we're doing is classifying or categorizing the different type of operators, which are really just the variables of any measurement, into these two categories. But once we know them, then we know that we can make a relationship between those variables, and we can lead to, later on we'll see that leads to things like the uncertainty principle and how those variables are tied together.